All right, so rotation. So far you've been learning that you have an object moving in in one dimension or two dimension. For example, a car that's driving, there's it's a linear motion, or you have a projectile that traces out XY direction and the horizontal direction. Now, in this chapter, what you're going to learn is that you're going to learn rotation. What is rotation? Something that rotates, right? So we know that that's what we call rotation, just like this. Okay, so we have something, so if I rotate this is what we call rotation. So there are several parameters that you need to be aware of when you're dealing with the rotation. And you can see that there's a lot of direct comparison between the rotation and linear motion. You've learned the three equations of motion for linear motion. Now what you're going to see is that for rotation, it also has the three equations of motion that you can use to help you understand the rotational motion of the object. Okay? So what are the quantity that we use to specify rotation? So first of all, if you look at this, when you trace out, when I push this on end, you can see that it traces out an angle. So this side, so when you go from this point to that point, let's say if I rotate it for 90 degrees, this is my starting. This is, I don't know what he went. Come. All right. So this is you're starting position. So if I push it, you're going to see that it's going to rotate. So let's say I rotate it for like 90 degrees, right? So this is my 90 degrees, a quadrant. But then if you look at this side, it traces out a length, the distance. So this is a circular arc. And the angle that that confines the circular arc is the angle theta. So in other words, you can see that the theta, the angle, and also this distance that it traces out at the end, that is actually related to each other. And the equation is this. So circular arc, the length of circular arc, we use the symbol S to indicate that. And then that's equal to, as I mentioned, this is the distance that traced out by the linear motion, and it's related to the angular angle theta. How are they related to each other? They are related to each other by a parameter, and this is what we call r. So S is equal to r theta. So you might wonder, what is your r? Your r is equal to the distance from the rotation axis to where you make the rotation. So in other words, if you look at this again, what is the rotation axis? When we say rotation axis, what does that mean? It means that that's something that does not move at all, and everything is moving about that point. Where is the rotation axis? Now with this. This thing, if you draw an imaginary line, this thing, this is a straight line, and then everything is rotating about that. And this line, this thing is what we call the rotation axis. For any rotation, there must be a rotation axis, and every point on this object is rotating about that rotation axis. Okay, so in this case, it is in the middle. So what is R? R is the distance between the rotation axis to the point. So this is your R here. So the angle, so the linear distance from this point to this point, which is the circular R, that's equal to the R, the radius, and then times the angle theta. Okay, this is how you relate. This is how you relate the distance traveled by the linear motion of a rotating body to the angular, this angular theta. Okay, so we can see that, for example, if we project this motion into x and y axis, and then let's say if we choose a point. So this is like a top view. You have a rotating object. So this is the top view, and then at one instance, it is at position theta 1. Okay? So let's say this is your theta 1. So this is your the reference point. And then at the next instance, it might travel to the next distance. So they trace out an angle that's called a theta 2. Okay? So in other words, this is the top view again. This is not the side view. This is the top view. So let's say you have a rotating object and you're looking at the reference point. So that reference point at T1, let's say at T1, it has making the angle theta 1 with the reference point, and then a later time, that's called that T2. It has rotated, that's a theta 2 angle. So in that case, what we can do is that utilize what we learned from chapter 2. In chapter 2, you find that when you have an object that travel from the position x1 to position x2 within the time interval t1 and t2, you can actually calculate the average. You can calculate, in addition to calculate average velocity, you can also find out what the displacement is, right? So let's draw analogies between the linear motion and the rotation. For example, in linear motion, we use x to indicate that's a position vector. When you talk about rotation, we use theta, the angular displacement. So in that case, angular position. So if you recall, how do we find the displacement? When object change from x1 to x2, how do you find displacement? What is position displacement? From x1 to x2, how do you find the displacement?
The square root of L to y plus L to x squared.
Huh? Oh, so I'm talking about, let's say, one-dimensional case. So initially at position x1, later you move to position x2. What is the displacement? x2 minus x1, right? Is that right? That's your displacement. This is, the difference between the two position vectors. So that's your x2 minus x1. That's your delta x. Okay, so this is displacement. Likewise, when you look at the projections of this rotational motion onto the x and y axis, let's say T1 is making the angle theta 1, and T2 is making the angle theta 2. What will be the angular displacement? So for the angular displacement, we use delta theta. How would you find this? So in other words, now your theta is not just an angle. You treat that as a vector. Okay? So how do you find delta theta, the angular displacement? That will be theta 2 minus theta 1, right? So you have theta 2 minus theta 1. You can see there's a direct one-to-one translation. So this is for linear motion, and this is when you have rotation. They are exactly the same. This describes linear motion, this describes rotation. So the angular displacement would just be the final position, angular position minus initial angular position, okay? Now if you recall, how do we calculate the average velocity for linear motion? To calculate the average velocity, if you remember, first of all, we find out what is the displacement over the time interval that the displacement took place, right? So this is the average velocity, and that's delta x over delta t. So in that case, there is actually a correspondent, velocity as well, but we don't call that velocity. We call that angular velocity. So everything about rotation is that there's the extra word angular in front of, let's say, position, in front of velocity, and later we'll find out there's for acceleration as well. So in that case, just by drawing analogy, what will be the average angular velocity? What would that be? Omega delta omega, the average. So this is what we call the angular velocity, and we call that omega, not w. So what is that? What would that omega be if you can do a direct, replacement? That would be delta theta over delta t, right? So you can see that rotation is basically a different way of, it's a linear motion. It's just extension. Instead of going forward, forward or backward, it's just, going in circles. So in that case, everything stays the same. All the equations that govern the motion stays the same, whether it's linear motion or rotation. They all have the same, same concept. Okay, just the symbol will be different. Instead of using delta x, you're using delta theta. Instead of using velocity v, you're using omega. Okay, now, so in that case, we know that your v is just simply dx over dt, the time derivative of velocity. So in that case, the instantaneous angular velocity can be found by by changing the delta to d, right? Because you just shrink the time interval so small that your delta now becomes d. So you have d theta dt. Again, as I mentioned, whenever you encounter this differential form, just take it as a fact. You don't have to really know how to do it just yet. Okay. All right. So what about the average acceleration? For linear motion, how do you find the average acceleration? Wouldn't that be delta v over delta t, right? So in that case, we also have a corresponding angular acceleration, and we call that alpha. Okay. So what would be the expression for our alpha?
Delta omega over delta.
Exactly. So you can see that whatever you learn from chapter 2 can be really applied to chapter 10 because they are exactly the same, except one is linear, one is in circles. Okay. So we have delta omega and then over delta t. Okay. So this is what we call angular velocity, angular acceleration, angular displacement, angular average velocity, and so forth. So you can see that there's a direct correspondence between all these parameters. And of course, your average, your instantaneous. So this is AVG, I forgot, right? So the average angular acceleration would just be delta omega over delta t. And to find instantaneous, of course, you just simply change that delta to d. So you have dv over dt on this side, and your alpha, instantaneous alpha, you have your d omega dt. And you'll find that for rotation, because it's rolling in two-dimensional case, so rotation actually has two different acceleration. And this one is d omega dt. So that's tangential component. You are going to learn that you already learned the other component that's actually in the radial case, right? That's a centripetal acceleration that you already learned. So all these two make up the accelerations for rotation. So since we are on to this, that's actually, we can take one step further. Let's say for the three equations of motion for linear motion, what are the three equations? Linear motion, three equations of motion. Okay, Vf equals Vi plus At, that's one. And then there's a square, right? So Vf squared is equal to Vi squared plus 2A delta x, for example, right? And what's the last equation? The final position is equal to initial position plus, what about this? Initial velocity times time, and then plus 1/2 At squared, right? Okay, so this is the three equations of motion that governs the motions when an object is making a linear motion. What about for rotation? You'll find that for rotation, as we went over this, you will realize that the equations for rotation will simply be the same scalar, the same equation, except that you have to change the variable. Okay, for example, your v now has to be changed to, the final velocity now becomes final angular velocity. So you have your omega f, that's equal to omega I, and then plus your At, instead of A, you're using alpha, exactly. That's your angular acceleration, okay? So likewise, for this one, you have omega f squared, that's equal to omega I squared, plus 2 times your A, again, is alpha. What about your delta x? That will be delta theta, okay? For this equation, that will be the final angular position, that's equal to initial angular position plus initial angular velocity times time plus 1/2 alpha and then t squared. So you can see that there's a direct one-to-one correspondence, except that you just have to realize that your x is now your theta, Your V now is your omega, and your A is your alpha. And so when you have an object that's in rotation, in a rotation motion, then this is the equation to use to describe at next instance what will be the angular acceleration B, what will be the angular position B. So all these equations, are the one that to use. Okay. So we mentioned about angular position, and so let's say if you have an object starting from here and then go from from this point and making a circular motion. So in that case, one revolution equals to how many pi? 2 pi's, right? That's common sense. Going from this point, you're making a 360-degree, so one revolution. So one revolution is equal to 2 pi, and that's also equal to 360 degrees. So based on that, you can actually find that. So it's 2 pi radians, and that's 360 degrees. So in other words, 1 radians, just based on this, 1 radians is equal to 57.3 degrees. That's equal to 0.159 revolution. Okay. Sometimes, most of the time, you'll be asked to see how many revolutions that the object has been rotating. Then you would need to know what 1 revolution is actually equal to 2 pi radians, and it's equal to 360 degrees. Okay. All right. So, any questions so far regarding how to find the angular velocity and also angular acceleration? Those are just by definition, because the rate of change. This is the equation that says the rate of change of angular position. So the rate of change of angular position, of course, that gives rise to the angular velocity. And the rate of change of angular velocity, that will give you the angular acceleration. So it's exactly the same as what you learned before. Okay. So what about direction? We know that if you have an object that's moving in this direction, that's considered positive. When you have an object that's moving in the leftward direction, that's considered negative. What about when you have an object that's in rotation? It's actually making that, like it has X and Y component. So how would you define the directions of the rotation? And this is, yes?
No, I was going to answer the question.
Now you can just answer the questions.
Is it counterclockwise positive, clockwise negative?
Yes, by convention, we define just like we define the right word is positive. When you're dealing with the rotation, counterclockwise. So CCW is what we call counterclockwise. It is considered positive. And then, so this is like going in this direction, that's counterclockwise. If you have a rotation that's going in this direction instead, so this direction is what we call the clockwise. For clockwise rotation, we consider that as negative. Okay, so this is how we define the angular position. So let's say if you have an angular position that's going in this direction, then that's considered positive. If that's going in the opposite direction, in the clockwise direction, then that's considered negative. Okay, so that's for position. What about angular velocity? When you have rotation, how do you know how do we define this? We know that numerically, the magnitude-wise, is a time rate of change of angular position. What about direction? What direction will be considered as positive? So again, because we're using counterclockwise for position for this angular position to be positive. So if you just look at your hands, okay. So if you have it like this, if you look at from the top view, your curved finger give rise to the counterclockwise. Follow the directions of the finger. It is counterclockwise. So your thumb gives you the directions of that velocity. Okay. So your angular velocity. What is the angle? What is the sign for the angular velocity? It's determined by your thumb. So when you have a counterclockwise rotation, you have a positive angular velocity. And if you have a clockwise rotation like this, so this is clockwise rotation, then the thumb is pointing downward. When you have a thumb that's pointing downward, that's considered negative. So how do we define? How do we find the signs for the angular velocity? When it's this way, it's positive. This way, that's negative. Okay? So it's defined by, it's consistent with that notation that counterclockwise is positive and clockwise is negative. Okay? So that's how you define the direction. Okay, so the next one, what we want to do is that we mentioned that linear motion and angular motion, they are related to each other. And this basically how they relate to each other. This is a distance traveled by the linear motion when the object is rotating through an angle theta. Well, that has a radius r. So let's look at this equation. If we take the time derivative on both sides, so you have ds over dt, and that's equal to, if we have, again, this is just for information, so you don't have to follow this procedure if you don't quite follow that, but it's the end result that you need to know. Okay, so if we take the time derivative on both sides and keeping the radius as a constant, so your r here, we keep it as a constant, and then you have your d theta dt. So let's look at this equation. That's based on that. We just take the time derivative of this equation, and we get that. What is our ds dt? Your s here is equivalent to x. So that's the distance in the linear motion. What is the ds dt? Time rate of change of position, that gives you velocity. So this is linear velocity. Okay? So that's equal to your r, and then d omega dt, that gives you time rate of change of angular displacement, angular position, that gives you omega. So this is the one equation you need to know. This is another equation that you need to know. That relates how the linear velocity to angular velocity, and that just equal to r times omega. Okay? So now, what about if we take further time derivative on this, what do we get? So we have dv over dt. That's equal to, we're going to keep r as a constant, and then you have your d omega, and then dt. What is dv over dt? Acceleration. So that's your instantaneous acceleration, and that's equal to r times d omega dt. That gives you alpha, exactly, angular acceleration. Okay, you can see that in linear motion, if you just add the word angular in front of the terms on the linear motion, that basically is the acceleration, angular acceleration, velocity, angular velocity, position, angular position. Okay, so this is another equation that you need to know, that your acceleration is equal to alpha times r, and this acceleration, as we mentioned, there are two components of the acceleration, and this component is what we call the tangential component, because you're taking the tangent part. This velocity is at the end point, so that's tangent to the circle. So that's your tangential component of the acceleration, which is alpha times r. What about another component of the acceleration? So if you look at this, this is something that's rotating, as we mentioned. It is rotating like this, so that, so this rotation is, this rotation is positive or negative if I rotate like that. If I rotate this way. This is clockwise or counterclockwise rotation? Counterclockwise, right? So in other words, if that's counterclockwise, your the angular velocity is pointing upwards, which means that it is positive. So it has a positive angular displacement and also positive angular velocity as well. Okay, and you can see that this is rotation axis. So this one is a rotation axis. This one in the middle that does not rotate, but other part of this body is rotating against this along this rotation axis. So from this central point to the end, that's your r here. Okay, so we calculate your velocity. If this is rotating at the rate that's if this is rotating at the rate that's omega, then you can see that the r times omega, that gives you velocity. So that velocity is how fast it is moving at this point. If you're looking at the velocity, angular velocity here is the same because they're all moving at the same angular velocity. But the linear velocity will be different because your linear velocity depends on the radius. So the velocity at this point And at the end point, they will be different because the radius here and as opposed to there is different. But omega stays the same, okay? And when you take the time derivative of that equation to give you acceleration, that acceleration is what we call tangential acceleration because the velocity is in this direction, so it's tangent to the circle. So that is your tangential acceleration, which is alpha times r. Now, we also mentioned that there's another acceleration that you have learned. What is that acceleration? What is that acceleration? Centrifugal acceleration. And how do we find the centrifugal acceleration? Is that just v squared over r? Right? Yeah, so this is what we call the radial part, the radial component of the acceleration. So in other words, when you have object that's moving in this direction, you have the radial part that's toward the center, so that's what we call the centripetal, and there's a tangential part, which is AT, and AT, of course, is alpha times r. And the radial component is v squared over r, which the v here is the same v here. So you have that. So you can actually replace your v with that expression to see what we get. So we have your r squared, omega squared over r. And what we get here is that the radial component has two expressions. If you are using the linear velocity, then that's just v squared over r. If you're using the angular velocity, then that's r omega squared. Okay? So either this or this. And it depends on what information you're given. And we utilize v equals r omega, that expression. Okay?